It's the most profound mystery in all of cosmology, an invisible force that makes up nearly 70% of the universe, and yet we have no idea what it is. It doesn't clump like matter. It doesn't glow, absorb, or scatter light. It's simply there, pushing, stretching, accelerating the cosmos. We call it dark energy, and it might be the key to understanding how the universe will end. The first clue came from an unexpected place: exploding stars. In the late 1990s, two independent teams of astronomers used Type Ia supernovae to measure cosmic distances. These supernovae are known as standard candles. Their intrinsic brightness is so predictable that any difference in observed brightness tells us how far away they are. But what astronomers found shocked the world. The most distant supernovae weren't as bright as they should have been. They were fainter, meaning farther away than expected. The universe wasn't just expanding, it was accelerating. Something was pushing galaxies apart, faster and faster. As time went on, that something was dubbed dark energy. But what is it? One idea is the cosmological constant, first introduced, then rejected by Albert Einstein. According to this idea, empty space itself has an inherent energy, a built-in pressure that pushes outward. But if this is true, the value must be incredibly small, many orders of magnitude smaller than what quantum field theory predicts. Another idea is that dark energy is dynamic, a changing field called quintessence, which varies over time and space. Yet another possibility, that our theory of gravity itself is incomplete. Perhaps what looks like acceleration is really the sign of new physics, a deeper understanding of space-time we haven't yet unlocked. Dark energy challenges our most fundamental assumptions about the cosmos. It's not just a mystery of matter, it's a mystery of existence. We know that it affects the large-scale structure of the universe. Without it, the mutual gravitational attraction of galaxies would slow down cosmic expansion over time. Instead, the opposite is happening. As dark energy dominates, galaxies are accelerating away from one another, leading to what some call the cosmic runaway. Eventually, this might result in a state where distant galaxies are moving away faster than the speed of light, not violating physics, but being carried by the expansion of space itself. If this continues, we may reach a future where everything beyond our local group disappears from view. A universe where the sky grows darker and emptier forever. But some theories go even further. They suggest a scenario called the Big Rip, where dark energy becomes so dominant that it tears apart galaxies, stars, planets, even atoms. This isn't science fiction. It's a mathematically possible endgame. But we're not there yet. Today, scientists are working tirelessly to measure dark energy more precisely. Missions like Euclid, the Nancy Grace Roman Space Telescope, and the Dark Energy Spectroscopic Instrument, DESI, aim to map the geometry of the universe, track galaxy clustering, and test expansion rates across cosmic time. These tools allow us to build a kind of cosmic history book, showing when and how dark energy began to dominate. If we can measure how it evolves, if it changes over time, we might finally distinguish between theories, and perhaps discover whether the cosmos is headed for a slow fade or a dramatic finale. The Triangulum Galaxy, like every other galaxy in the universe, is a participant in this vast expansion. Its light may one day fade into invisibility, not because it died, but because the universe pushed it beyond reach. Even now, it's part of the silent contest between gravity and dark energy. Gravity pulls inward, dark energy pushes outward. The future of the cosmos depends on which force wins. And remarkably, it seems dark energy already has. That raises deep questions. Is dark energy a property of space itself? Is it connected to the vacuum energy predicted by quantum mechanics? Or is it something entirely unknown, a fifth force? Could it change, disappear, reverse? These aren't just mathematical puzzles. They are questions about our fate. Will the stars continue to shine forever? Will galaxies remain visible to each other? Or are we living in a brief window of cosmic clarity, soon to be isolated by an accelerating universe? Every time we measure a supernova, every time we chart a galaxy, every time we test the shape of space, we're not just studying physics. We're trying to understand what kind of story the universe is telling. A story with a beginning, a middle, and one day, an end. And in that story, dark energy might be the final chapter, or the key to a sequel we cannot yet imagine.